I'm Carly Wingness, and I'm an aerospace engineer.
Hi there, I'm Aiden Clare, and I'm a mechanical engineering student.
Hi, I'm John Dominguez Trujillo, and I'm a mechanical engineer.
Hi, I'm Matthew Colson, and I'm a software engineering student.
Hi, hello, my name is Diego Glenn, and I am the systems engineer.
Hi, my name's Amber Parker. I'm a software engineering student.
Right, we just hit something on the taxiway. Could you tell us what it was?
The whole tail of that CRJ's off. Yeah, we got the CRJ 900 with its tail off here off of Foxtrot 2.
Both planes belong to Delta Airlines, and it's the large plane coming towards the camera that doesn't see how the tip of its wing is about to break off the tail of the smaller jet.
As airports have become more crowded, the need for pilots to have an increased situational awareness when performing ground operations to eliminate ground collisions between aircraft has become more apparent. To combat this, working alongside Parker Meggitt, we have worked to design CASA, which stands for Camera for Aerospace Situation Awareness, a simplified aircraft model capable of presenting the capabilities of a 360-degree bird's eye view that can be altered and upscaled to fit the needs and requirements of customers.
To accomplish this mechanically, we needed to design a 24 by 24 by 12 inch simplified aircraft that weighed below 20 pounds with easy to access internals. Due to this requirement, we decided to 3D print the structure to ensure that it is lightweight and easy modifiable to change the camera positions if needed. The cameras had to be contained within the model, so our hardware fittings had to have strict tolerances so that the software calibrations did not shift. The camera positions were decided using a frame of view simulator that stitches the theoretical FOV of each camera has on our SolidWorks model. Our electronic selections were simple and carefully chosen to fit within the body of the plane. We chose the Jetson Aura Nano for its larger computing power compared to similar modules. This helps with the image stitching and processing. The Jetson allows for 2 USB Type 2 and 2 CSI connected cameras. Our cameras have wide-angle fisheye lenses so that we can use as few cameras as possible while still maintaining the 360-degree coverage. We are using a fully self-contained lithium-ion battery pack to charge our components, which has an estimated runtime of around 2.5 hours. Finally, to make our product even better for our sponsors, we added a Wi-Fi card and antennas to be able to transmit our camera views wirelessly to the display. There were a few setbacks in designing and integrating our model. Our first plane iteration did not have manufacturability in mind. The designs were changed to make prints easier and faster. However, each printer that we used had different tolerances, and due to the tight tolerances needed on our electronics, many iterations of prints had to be performed. The final mechanical product is now a fully snap-fit plane that securely stores all our hardware inside.
The software for the CASA system is written almost entirely in 9,000 lines of Rust, a modern programming language designed for maximum performance, reliability, and productivity. We utilized a common asynchronous runtime for Rust called Tokyo, which allowed us to write highly concurrent and parallel software in a simpler, linear manner. Additionally, we used long-running tasks that communicate over asynchronous channels for repeated or time-sensitive processes, similar to an after model. The backend follows a hierarchical structure, the top of which is an HTTP web server that serves static assets for the front end, the WebSocket endpoint for the video stream, and an API to adjust system settings. The server has an atomically shared struct, which contains the channels necessary to receive completed frames and send updates for stitching and object detection settings. Running in the background are a few tasks that support this process, the most important being the rendering loop. It repeatedly checks for any desired updates, loads camera frames, requests the rendering of the main view, compresses the image, and finally sends the result back to the WebSocket host for delivery to the client. Each camera is also given a task, which we call a cam loader. Since our system supports multiple types of camera backends, including the static image, video for Linux, NVIDIA's libArgus, and a colored grid pattern, this gives us a simple abstraction that provides enhanced flexibility and performance. The rendering loop simply sends a request with a buffer, and the cam loader sends the buffer back with the new image. The rendering process then utilizes WGPU to create and run graphics pipelines with the WGSL shaders we created to implement the core of the projection and stitching algorithm. For our system, the rendering also needs a way to detect objects around the plane. We use TensorRT to execute the AI models while harnessing as much of the Jetson's neural capabilities as possible. However, this requires a way to adapt CUDA into our system. To accomplish this, we use another task that hosts the CUDA buffers and TensorRT runtime. It concurrently requests stitch views for multiple directions, runs the AI model against each of those images, and creates 3D vertex positions that represent the detected bounding boxes. The vertices are given the color red if their respective bounding box lies between the wings in front of the vehicle. Otherwise, they are yellow. Another task exists to repeatedly handle settings changes, start the detection process, and forward the vertices to the rendering loop so they can be displayed to the user. In this initial prototype, the AI model we used to find these bounding boxes was YOLO V11, which is a simple, general-purpose object detector. It can detect and classify 80 different common household objects and finds the class, confidence, and location of the object, which is typically referred to as a bounding box. The system's front end is a simple HTML, CSS, and JavaScript web page that connects to the video WebSocket endpoint of the back end and renders the image to a canvas. The images are compressed with the QoI algorithm to reduce the required transmission bandwidth while maintaining simplicity and speed. Finally, the UI buttons simply cause API requests to the corresponding back-end endpoint with the new value. Our software is the most vital part of our system, and our decisions throughout the development process have helped us create a simple yet effective solution to our complex problem.
Here we have our test setup, which started off with a grid pattern at the bottom of the plane.
This was to allow us to calibrate the bottom camera for a better stitched image. We did our testing in a lounge that had fluorescent overhead lighting, which was one of our requirements. The goal was to have 6 or more objects around the table surrounding the plane. This consisted of mostly chairs and dry erase boards. The objects with the yellow bounding boxes represent objects detected behind the wings, and the objects with red bounding box represents objects in front of the wings. Here we have the graphical user interface, or GUI, that allows us to change views between top, down, bottom, and right simulated camera view.
During test and integration was when we learned the most about engineering. Seemingly endless flaws in our design smacked us in the face repeatedly, and new ones popped up when we tried to fix the old ones. This taught us the value of iteration and simplicity in our designs. We learned that sometimes band-aid fixes are okay, but most of the time they're not. Too many band-aid fixes to a design leads to shoddy complexity. When faced with printing our second design, we realized that our day-long 3D prints for half a dozen different parts was just unacceptable. So we redesigned the entire mechanical subsystem. This daunting task took over 50 hours, but it had massive payoffs as we continued to iterate our design. Our 3D print times were cut in half after our redesign, and the integration between mechanical and electrical hardware was greatly simplified. This third design's success was impossible without the hindsight from our first 2 designs, hence the value of iteration and simplicity.
In the future, CASA can be improved by adding more cameras to eliminate all blind spots and further increase situational awareness. Also, CASA can be optimized to reduce latency and increase frame rate consistency by implementing more sophisticated video compression. Lastly, CASA can be developed into a mobile app for pilot convenience, take advantage of cloud-based image logging to allow for local and global records of any evidence in the case of a collision, and could allow for the integration of inertial measurement units for further improvements. Finally, we want to say thank you to our mentor, Jim Sweetman, for his support and guidance, Parker Mediot for their constant support and confidence, and the University of Arizona Engineering Department for making this opportunity possible.